This problem comes to us from our textbook, Thomas's Calculus, in its 14th edition. We're asked to use the shell method to find the volumes of the solids generated by revolving this region around these different axes of revolution. In this video, I only want to do parts B and D as examples. Not a bad idea at the end of the video to give parts A and C a try. They involve the same kind of process, the same kind of thinking. But let's go on and get started by finding the volume of the region formed by, the volume of the solid formed by revolving this region around the line y equals 2. So we'll get started by thinking about revolving around this line. So in the shell method, I need to remember that I always think about my shells being parallel to the axis of revolution. I always like to draw a little rectangle down here because I'm going to form my shell by revolving that rectangle around. And so the height of the shell would be a right function minus a left function, and then I'll also need to know a shell radius because, of course, to find this volume, I'll be thinking about integrating 2 pi times the shell radius times the shell height, and I'll be integrating with respect to y. Well, I see that my shell radius is the distance between this horizontal line at y equals 2 and where this particular rectangle is. Well, the rectangle itself is just some height above the x-axis, so that's the y-coordinate, and so that distance would be 2 minus y. Now I need to think left function subtracted from the right function. So the upper function minus the lower function, because we're with respect to y is really a right function minus a left function. So that's a y squared over 2 minus this other function, y to the 4th, over 4 minus y squared over 2, integrating with respect to y. All right, and let's see, where does our region start? Down here at 0, and then it ends at that point up at 2. Coincidentally, that's where we're also revolving around. All right, we've set up our definite integral. Now we just need to do some arithmetic, and then we need to find an antiderivative. Let's go on and write that 2 pi out front. All right, in the second set of parentheses, I can do some simplification. I have a y squared over 2 minus a minus y squared over 2. It's really adding 2 of those together, minus y to the 4th over 4. Let's multiply these two binomials together, and then we will be ready to evaluate this definite integral. 2y squared minus y to the 4th over 2 minus y cubed, and then plus y to the 5th over 4. All right, and of course we're still integrating with respect to y. We're ready to find our antiderivative. Let's see, 2/3 y cubed minus y to the 5th over 10 minus y to the 4th over 4. And this one's going to be plus y to the 6th over 24, evaluated from 0 to 2. So let's see, we need to plug a 2 into all of these places and see what happens. So let's see, that's going to be a 2 pi times 2 to the 3rd is 8, so 16 thirds. 2 to the 5th is 32, so that's minus 32 tenths. That's going to be a 16 over 4, which is just a 4. And then finally, we have to think about 2 to the 6th, which would be 64. And then I only managed to reduce that one, though I probably should have done that one and that one. But what I really need to do is add all those together and multiply by 2 pi. And when we do that, we're going to get 8 pi over 5. And there's our volume in part B. So now, let's see if we can hop down and do part D. In part D, we're asked to revolve around the line at y equals minus 5/8. So let's imagine extending our x-axis down and having minus 1 be about there. So minus 5/8, some horizontal line. Oh, maybe we just say about there. So the same method applies. Still have a horizontal axis, so I'm going to think about revolving that shell around. Well, this distance up would be y. This distance down is 5/8, so the shell radius altogether is y plus 5/8. I could also think about that as a y minus a minus 5/8, right? A top location minus a bottom location. The shell radius is not going to change from part B. It's still the right function minus the left function. So knowing this shell radius, we're ready to set up this definite integral. All right. Our region still starts at 0 and ends at 2. 2 pi times the shell radius times that shell height. And I'm going to write out all the details, even though we've already simplified this from our last problem, so we could actually shorten up the work here just a little bit by at least one step if we would just take a peek over at how this combined up. But I'll just do it again for the heck of it. All right. Now we need to multiply this out, and from there we'll be able to find a definite integral. So let's see, we have a y cubed minus y to the 5th over 4 plus 5/8 y squared, and then finally minus 5 y to the 4th over 32. All right, let's find our antiderivative. Let's see, a y to the 4th over 4 minus y to the 6th over 24. I see how similar this problem really is to the last one, plus 5y cubed over 24. And let's see, minus 5y to the 5th over 32 times 5 is 160. Evaluated from 0 to 2. Plugging in the lower bound would be very easy, so I really do just need to worry about plugging in that 2. This time I'm not going to worry about simplifying or reducing anything, just thinking about these powers of 2. Plus 40 over 24. And that one, oh, that actually works out really nice. That one would definitely reduce. And then I'm going to pretend to do all this arithmetic in my head and not just look at the sheet that I've prepared before I did the video. And I find out that that gives me a volume of 4 pi. All right, there we have it. Solutions to part B and D of this problem from section 6.2 of Thomas's Calculus. And that's it for now.